All right, let's get started. 3.8. 3.8 is not teaching us anything new. 3.8 is just going to introduce you to more complicated problems, harder problems. The type of problems that we'll be seeing in physics. So it's no new lesson, just harder problems. Okay. Now the problem with these harder problems is there isn't any, this is how you solve it. Okay? The way the problems are going to work, you're going to be given a big paragraph that describes something. You have to internalize that, understand it, internalize it. Typically you set up a drawing representing what you know, or represent a drawing of this scenario, represent the information that you've captured, and then you just got to figure out how to solve the problem. So there's no tips, there's no tricks. Well, the author lays out some basic stuff. He says, draw a picture, write down the numerical information, write down what you're asked to find, basic stuff like that for how to solve the problem. But outside of really generic stuff like that, there's no way for me to tell you how to solve these problems. Okay. So you've just got to wrestle with the problems, figure it out, solve it. All right, so let's do one to give you an example of what I'm talking about. A water runs into a conical tank at a rate of 9 feet cubed per minute. Conical meaning it's cone-shaped. Okay? So I know that it runs in at 9 feet per minute, 9 feet cubed per minute. So already in my head, my volume is changing with respect to time at a rate of 9 feet cubed per minute. Just reading what it says. Okay. The tank stands pointed downwards and has a height of 10 feet and a base radius of 5 feet. So our cone that we're using, so we got some cone, it's pointed down. This is what the water's running into. At the top of the cone, we have a radius of 5 feet, and the height of the cone is 10 feet. Okay? So the water level is going to be somewhere in, like right here. Here's the water level. I don't know how high the water level is. We'll just call this Y. And it will have its own little radius for how much the water is filling up, R. So that's how much of the cone is full of water. Not sure. I know how fast the water is going into the cone. And here's the whole cone. Understand the picture so far? Mm-hmm. Okay. How fast is the water level rising when the water is 6 feet deep? How fast is the water level rising when the water is 6 feet deep? So I am looking for dy dt. This is what I'm looking for. Okay. How fast, because y I'm using to represent my water level, when y is equal to 6 feet. Okay? So have some of my basic information right there. Okay, so let's get started on this problem. First off, the volume of the water is equal to, we know the volume of a cone formula? I don't. 1/3 the area of the base times the height. Same as the area of a cylinder times 1/3. Okay. Or not the area of a cylinder, the volume of a cylinder. So what's the volume of a cylinder?
1/3 the base.
No. Volume of a cylinder.
I don't know the volume of a cylinder.
What? What's the volume of, you don't know the volume of a cylinder? No. Holy cow. Okay, what's the area of the base of the cylinder? This is radius R.
The area of the base?
Yeah.
Just a circle, right?
Yeah, which is?
Which is 2 pi r.
Holy cow. Pi r squared.
Oh.
First off, you understand that areas have to be squared, right?
Yeah.
If I say, what's the area of this room, and you say 127 feet, that doesn't make sense. 127 feet squared makes sense. 127 feet doesn't make any sense.
Okay.
So areas have to be squared. So if my radius, so I have my radius for this, whatever the area of my circle is, better have a radius squared. So if my radius is 5 meters, then my area is pi times 25 meters squared.
Okay.
So anytime you're calculating an area, it's going to have a squared in there. What's the area of a rectangle?
Just width times length.
Sure, base times height is how we usually say it. But there you go. It has to have two things that we're multiplying together. Volume has to have 3. What's the volume of a square?
Yeah, depth, height, and width.
Yeah.
Yeah, whatever the length is, cubed. X cubed. If you use that as the length of the cube. Okay? So areas always have to have squares. Volumes always have to have cubes in their formulas. So there's just one way that you should have instantly thrown out that answer. But pi r squared, that's the area of a circle.
Okay.
Okay? So, what's the volume now of this thing? If this is height h,
It's just pi r squared times h.
perfect.
Cubed.
No, just times h. Notice now we have a cube. Look, if that's 5 meters and that's 10 meters, 5 meters cubed, that's 25 meters squared, times another 10 meters, would equal 250 pi meters cubed. We now have meters and meters squared.
Oh, I see.
Put them all together, meters cubed. Okay, volume of a cone, or of
Cylinder.
a cylinder, right there. The volume now of a cone with these same dimensions, just now cut a cone out of that thing, is just 1/3 that.
Why is it 1/3?
We don't have time to derive all this. I mean, we should really go all the way back to the circle. But we got to focus on the problem at hand. Okay. So, go learn some basic formulas. Some basic geometric formulas. You guys should know these. You should know these just fine.
Geometry was a mess for me.
Huh?
I said geometry was a mess for me.
Yeah, geometry is a mess for all kids nowadays. So, yeah, gotta bite the bullet.
Okay.
Anyways, so what is the volume of this now? So the volume of the water is equal to, we have 1/3 pi r squared times y.
Okay.
You with me so far?
Yeah.
Okay. Now, notice that we know a relationship between y and r because I know the shape of this whole thing.
Okay.
Notice that the whole cone is 10 high when it has a radius of 5. So what's the relationship to of the height to the radius?
1/2.
The radius is 1/2 the height.
Okay.
Is that always the case?
So I know it is for this cone.
Okay.
So I know that r is 1/2 y. Right?
Yeah.
So I can write this equation without, I can replace all my r's with y's or all my y's with r's, however I want to do it. I want to replace all my r's with y's because keep in mind, I want dy dt.
Okay.
Okay? So this is the same thing as v is equal to 1/3 pi y halves squared times y. With me?
Mm-hmm.
Just algebra now, and I square that, that's going to give me 1/4. Combined with that, we have pi 12s. That's that. 2, 2, 3 gives me 12. Pi y cubed. Right?
Yeah. How'd you get the pi on top of the 12 then?
Oh, I was just moving it all together, all my constants together, so y cubed. Sorry.
There you go.
Didn't mean to have 2 pi's. Good? Okay. Now, implicitly differentiate with respect to time.
Okay.
So, dv dt is equal to pi 12 times, what's the derivative of this?
3y squared.
3y squared times dy dt,
Yeah.
right? Took the derivative of both sides with respect to time.
Okay.
Now I know what dv dt is. It's 9.
Yeah.
So I now want to solve this when y is equal to 6 feet for dy dt.
Okay.
With me?
Yeah.
So 9 is equal to 12 and 3 go out, leaving 4. So pi over 4 times 6 squared times dy dt. Follow me there?
Mm-hmm.
Okay. Let's see. Multiply 9 by 4 makes it 36. But then divide both sides by 6 squared is divided by 36. So I'm going to get 1 is equal to pi times dy dt. Follow that?
Yeah.
9 times 4, when I multiply both sides by 4, 9 times 4 is 36. Then divide both sides by 6 squared, which gives me 1. So, dy dt is equal to 1 over pi feet per minute. That is the rate at which the water level is rising.
Okay.
Okay?
Okay.
Kind of weird. Nothing that you haven't seen before. It's just a more involved problem. So let's do another one. So the next one, a hot air balloon rising straight up from a level field is tracked by a rangefinder 150 meters from the liftoff point. So my hot air balloon, here's its liftoff point. It's going to be going up from there. 150 meters over. So this is 150 meters. Here's our tracking point. So hot air balloon's going up. We're tracking it from here. And the hot air balloon we know goes straight up. At the moment, the rangefinder's elevation angle is pi force. So our hot air balloon is rising. Here it is. And we have our rangefinder located right here. Okay, here's our angle theta. So we're saying when theta is equal to pi force. So let's read again. At the moment the rangefinder's elevation angle is pi force, the angle is increasing at a rate of 0.14 radians per minute. Okay, so the rangefinder, it's pointing at this thing, so the angle is getting bigger and bigger as the hot air balloon rises, right?
Mm-hmm.
And so we know that our change in our angle with respect to time is equal to 0.14 radians per minute. Good?
Yeah.
Okay. How fast is the balloon rising at that moment? So how fast is the balloon going up? So we'll call this height, the height of the balloon, y. Good?
Yeah.
And so we want to know dy dt now. I want to know how fast is the balloon rising
Okay.
at this moment. Good?
Yeah.
Okay. So now we're kind of stuck. We need some sort of equation, some sort of relationship between theta and how high this balloon is.
Okay.
Well, what can relate theta to y? Think about our trig identities.
Sine.
Sine could, cosine could, any of them could really. But notice that this length is a fixed length. So we probably want to use that. And so I'm going to use tangent. So tangent of theta is equal to y over 150.
That's radius.
Rise over run, right?
Yeah.
Or we can say y is equal to 150 times tangent of theta. Right?
Okay.
So now, let's take the derivative of both sides with respect to time. So dy dt is equal to 150 times, what's the derivative of the tangent of theta?
Secant squared of theta.
Secant squared of theta times what?
The rate it's going up.
No,
No.
it's
Chain rule.
What?
Derivative of the outside times the derivative of the inside.
what's the inside one though?
The inside one's just theta.
So what's the derivative of theta?
Yeah, exactly. What is d theta dt?
Oh, I see.
Remember, we're doing the derivative with respect to t.
Yeah.
If we were doing the derivative with respect to theta, we would have been done, because it would have been d theta, which is 1. You don't have to put the 1.
Okay.
That's the derivative with respect to time.
And we already know that.
And we already know that.
Okay.
So, dy dt is equal to 150. We want it when theta is equal to pi fourths. So what's secant of pi fourths?
I don't remember that.
What's secant? It's 1 over
1 over sine or cosine?
cosine.
Cosine.
What's cosine of pi fourths?
2 over root 2.
Root 2 over 2.
Root 2 over 2.
So 1 over root 2 over 2 is going to be
1 over root 2 times 2.
Can you write it out?
so 1 over root 2 over 2 is equal to
2 over root 2?
2 over root 2, sure, which is equal to
I don't know what that's equal to. Isn't that simplified all the way?
no. What's another way to write 2? 2 is what squared?
Root 2.
Root 2 squared. So I can write this as root 2 times root 2 all over root 2, which is equal to
Root 2.
root 2. There we go.
Oh, what the heck?
So, secant of theta is equal to root 2. So secant squared of theta is equal to
2.
2. All that times 0.14, right?
Mm-hmm.
Which is going to be equal to, I don't know, what's 300 times 0.14? I need to start bringing my calculator.
It's 42.
42?
Mm-hmm.
Take your word for it. I assume that had a rounding error.
No. Came out exactly.
Exactly 42.
You did it right.
42, and this is going to be meters per minute. Check the answer with the book. Yep, 42 meters per minute. So we did it.
Okay.
All right. Another one?
Yes, please.
Mm-hmm.
Next one. A police cruiser approaches a right-angled intersection from the north and is chasing a speeding car that has just turned the corner and is now moving straight east. So, we've got some right intersection like this. We've got our police cruiser right here, and it's going this way. And then we've got some other car running away from the police cruiser, and it's going this way.
Wasn't the police cruiser going north?
Coming from the north.
Oh, I see.
When the cruiser is 0.6 miles north, so this is 0.6. Cruiser is 0.6 miles north of the intersection. The car is 0.8 miles east. the police, the police determine with radar that the distance between them and the car is increasing at 20 miles per hour. The cruiser is moving at 60 miles per hour at the instant of the measurement. What is the speed of this car? Okay, so we'll call the police's car here this distance y. We'll call this distance here x, right?
The distance, we already have the distance?
It's changing with time now. This is just a particular instant of measurement. These aren't holding still.
Oh, okay.
Okay? So, police car is y. We know that the police car is moving 60 miles per hour. That means dy dt is equal to what?
60 miles per hour.
No. It's equal to negative 60. Why negative?
Because it's coming closer.
Because it's going this
down.
way. We're calling that way positive y. So this distance is getting smaller and smaller and smaller.
Okay.
Right?
Mm-hmm.
On the other hand, this distance is getting bigger and bigger and bigger. So keep track of that. Okay. I think we have all our information up here. Oh, the thing that it said is the distance between them is increasing at 20 miles per hour. The distance between the two cars is increasing at 20 miles per hour.
Okay.
Yeah.
So we need to capture that distance. So we'll say the distance between the two cars, we'll just call that S. Good?
Okay.
And the SDT, I know is equal to 20.
Mm-hmm.
So what are we looking for?
We are looking for this car's speed.
Okay.
So we are looking for, with how we have this set up, dx dt.
That's right.
Okay. So, what is S? S, the distance between the cars, is equal to just the distance formula, square root of x squared plus y squared. Right?
Mm-hmm.
What's that? Like, where'd you get that from?
Pythagorean theorem.
Oh, you're right.
Good?
Yeah.
All right. So now, take the derivative with respect to time. Let me rewrite this one more time. S is equal to x squared plus y squared to the 1/2.
Okay.
So now, take the time derivative. So ds dt is equal to, what's the derivative of x squared?
2.
Oh, sorry, we got to do chain rule first. So derivative of the outside, so 1/2 x squared plus y squared
Negative 1/2.
to minus 1/2, perfect. Times now the derivative of the inside. So the derivative of this is
2x
times
times
dx dt.
dx dt.
We're not taking the derivative with respect to x, we're taking the derivative with respect to t.
Yeah.
So you have to use a chain rule.
Okay.
Plus the y, right?
Plus what?
2y times dy dt.
Perfect. Okay. Now, we're looking for it when x is 0.8, y is 0.6, dy dt is negative 60, and ds dt is 20.
Okay.
So just
So, 20 is equal to, notice the 2, and the 1/2 all cancel out.
okay.
Follow that?
Yeah.
And in fact, 0.6 squared is
0.3, right?
0.36. 0.8 squared is
0.64.
0.64 plus 0.36 is
100 or
1. So these two things squared is 1. 1 over the square root of 1 is still just 1. So this whole thing right here is just 1.
1. Okay.
So the 1/2 cancels out with those 2's, and this is just 1. So we're left with just x times dx dt plus y times dy dt. Oh wait, we have one of these. We have dy dt. Y times, oh, and we have x.
We have x and y.
So x is 0.8. So 0.8 times dx dt plus y is 0.6 times negative 60 is equal to 20, right?
Yeah.
And we're looking for the dx dt. So 20 is equal to 0.8 dx dt minus 36, right?
Yeah.
Move that over. We have 56 is equal to 0.8 dx dt. Divide both sides by 0.8, and we get 70 is equal to dx dt. So 70 miles per hour is how fast this car is moving.
Okay.
Good?
Yeah.
Want more examples?
Yeah.
It'd be
Alright.
nice if we were the ones doing it.
We'll do one more.
Okay.
So, I'm not sure which of these are going to be the hardest. Should we just assume the last one's going to be the hardest?
Why not?
All right. Looks the most complex. So the last one. This one, figure 3.37a shows a rope running through a pulley at P and bearing the weight W. So we have a pulley here holding up some weight W. And then this comes back this way to here, where it's being held by some man. The hand of a worker. Okay, so let's keep reading. Figure 3.37a shows a rope running through a pulley at P, bearing the weight W at one end, and the other end is held 5 feet above the ground in the hand of M. So we've got some guy here holding this, and he's doing so 5 feet above the ground.
Don't you have your P variable?
P is that point right there, P for a pulley. Good?
Okay.
Let's see. Suppose the pulley is 25 feet above the ground. So let's put a ground in our picture. You can be on ground. Okay. Suppose the pulley is 25 feet off the ground, the rope is 45 feet long, and the worker is walking rapidly away at a rate of 4 feet per second. How fast is the weight being raised when the worker's hands is 21 feet from here? So we'll call the distance from here to our worker, call that distance x. Good?
Yeah.
We're looking for dx dt. Oh wait, dx dt was given to us.
Yeah, it's 21, right?
Dx dt is 4 feet per second
Oh.
when x is equal to 21 feet. Okay? We'll call the height that the weight is in the air. This triangle actually, we'll cut off 5 feet from it, so we'll look at this triangle right here. See the triangle I'm making?
Mm-hmm.
So I'll call the distance from the weight to here y. So this whole distance is 20,
Okay.
right?
20.
Yeah.
Okay, so now I know the length of the rope. So the length of the rope is 45 feet. What is the length of the rope? Let's call this side of the pulley R.
Okay.
This length. So R plus 20 minus Y is equal to 45. Make sure you follow that.
Yeah.
20 is this distance, minus Y is just portion with the rope. So 20 minus Y is this, and R is this. So R plus 20 minus Y together gives me the total length of the rope, which is 45.
Okay.
So I know that, and then I also know that for my triangle, this side squared plus this side squared equals this side squared. So I also know that R squared is equal to X squared plus
20 minus
20
Y.
squared.
Oh.
No, because we need the whole triangle.
Yeah.
So this side of the triangle doesn't change.
Okay.
But this side and this side do, as this guy walks away. Okay. So what are we looking for? How fast is the weight being raised? Oh, so we're looking for dy dt. So I want to know how much the weight is going up as this guy's walking away at a rate of 4 feet per second.
Okay.
Make sense?
Mm-hmm.
Okay, so the R is what I want to get out of the equation. So I'm going to solve this for R and then make a substitution into this.
Okay.
So from this, I know that R is equal to 25 plus Y.
Mm-hmm.
So then taking this, I have 25 plus Y squared is equal to X squared plus 20 squared. Right?
Yeah.
Square this out, we get 25 squared plus 50Y plus Y squared is equal to X squared plus 20 squared, not 20 to 0, squared. Right?
Mm-hmm.
Okay, now take the time derivative of both sides. No derivative with respect to time.
Of both sides?
Yeah. What you do to one side, you got to do to the other. You can't just take the derivative of this side and say it's equal to this.
Yeah.
That doesn't make sense. So, what's the derivative of 25 squared with respect to time?
50?
0.
0. It's just a constant. 25 squared, that's just some number.
Yes.
The beauty of implicit differentiation. We don't even have to deal with these big numbers. So that's 0 plus
50
50
dy dt.
times.
dy dt. Yes. Plus
2y dy dt.
is equal to
2x 2y dx dt.
perfect. Okay, we're solving for dy dt, so let's factor that out. So I know that dy dt times 50 plus 2y is equal to 2 times, we're trying to figure out when our x was 21 feet,
Okay.
so 2 times 21 times our dx dt is 4. So dy dt is equal to, we can divide both sides by 2. So if I divide 2 by this, I'm left with a 25 and 1y.
Mm-hmm.
And divide this by 2, and we're just left with 21 times 4. So 21 times 4 is 84. Divided by, we factor a 2 out of this, so we're going to have 25 plus y. Right?
Yeah.
We need to figure out y. So when x is 21, what's y? How am I going to figure that out? What's the easiest way? Probably just this equation to get r, and then this equation to get y. So let's figure out what r is when x is 21, and then we can figure out what y is.
Okay.
Okay, so I know that r squared is equal to 21 squared plus 20 squared, right? So r is equal to 29, I think. Want to double check that for me? 20, 21, 29, I think is a Pythagorean triple.
What?
20 squared plus 21 squared is 841. Square root of 841 is equal to 29. Okay, that's right.
Okay.
So, r is equal to 29, so y then is equal to
4.
4. So come back in, plug in 4 here. Yeah, right?
Mm-hmm.
Yeah.
So this is equal to 84 over 29, which is going to be roughly 2.3. 2.3 feet per second. Let's check the answer. 2.9. 84 divided by 29. Did I type that wrong? Oh, yeah, oops. Okay. So 2.89 or 2.9. Okay. Just putting into my calculator wrong. Okay. So there we go.
Gee.
So that's 3.8, just a bunch of problems like that you have to solve.
Okay.
Good?
I hope so. That's rough.
Yeah. They expect a little bit more of you.
And this is what we're going to be doing in physics just all the time?
Yeah, problems like this all the time, where you just read a little description of some sort of physical phenomena and solve for something happening. Yep, very common.
Are we going to do any labs on physics?
No.
Just go through it rigorously?
Yep.
Not even gonna drop rocks off the school.
No. Something tells me you can pull that one off by yourself.
Yeah.
Okay.
Okay. So, 3.9 is about linearization of differentials. Linearization and differentials. So first linearization, then we'll talk about differentials. What's linearization? Linearization, we have already been doing it. It's just finding the tangent line. Okay? So it's just a fancy way of saying finding the tangent line. So when you have some curve, so we've got some curve going along, and we say, what is the linearization centered at this point, x equal to a? What is that? It's the tangent line that goes through that point. That is all that it is.
So what's the point in the section then?
So linearization, the point of the section is that when you do this linearization, when you come up with this tangent line, then as long as you stay close to the point A, then this tangent line approximates your curve here. So as long as you stay close inside of A, then it acts as a good approximation. So this section is going to be focused largely on approximations.
Okay.
And how we can work with approximations. Now, for the examples that we actually work, you'll feel like, why am I doing this? There's no point. Real life, what is this useful for? It's when your curve is hard to work with, but the linearization of it is real easy to work with because it's just a line.
Okay.
So you can work with the line and get approximations which are good enough for whatever problem you're trying to solve. Okay? So, let's write out the actual definition here, and then you'll see how we've already been doing this. Definition. If f is differentiable at x equal to a, if f is differentiable at x equal to a, comma, then you're approximating, oops, that's approximation, I jumped ahead in reading. Then the approximating function, L of x equal to f of a plus f prime of a times x minus a is a linearization. Of f at a. So, in other words, close to a, the point is that f of x can be roughly approximated by L of x. L of x is the line. Okay, notice how this is just the equation of a line going through this point.
Yeah.
Because that's a, this height right here, this is f of a. So the equation of a line going through that point, we have y is equal to y1 plus m times x minus x1. See how this is just the equation of a line we've been using the whole time?
Mm-hmm.
I think if you get that, this whole section, well, the first half of the section becomes real easy. You're used to y minus y1 is equal to m times x minus x1, right? This is the equation of a line that passes through the point x1, y1.
Mm-hmm.
That's the same as y minus, if we're talking about this point, then our y1 is f of a. Y minus f of a is equal to m, what's our slope? It's just the derivative of the function at that point. This is f. Then the slope at that point is f prime at a times x minus x1 is a. Or in other words, y is equal to, if we move this to the other side, f of a plus f prime of a times x minus a. Does that make sense?
Yeah.
Okay. So, if you get the linearization is just finding this tangent line, then I don't think you'll have much trouble solving these problems. So let's do an example. It says find the linearization of f of x equal to the square root of x plus 1 at x equal to 0. What are we looking for? The tangent lines of this at this point. That's it.
Okay.
So first off, let's find f prime at 0. We can start with f prime of x and then plug in 0. So let's just do f prime of x real quick, what's that equal to?
1 over,
Let's write this another way. Remember, f of x, we could also write that as x plus 1 to the 1/2, right? Okay, so what's the derivative?
is
1/2 x
1/2
x plus 1 to the power of negative 1/2 multiplied by 1.
no plus, right?
Plus what?
Plus 1.
Plus 1? Where are you getting plus 1?
The derivative of x plus 1 is just 1.
The derivative, so you multiply by the derivative of the inside.
That's right.
And when you multiply it by 1, it doesn't change it.
So it's just that?
So it's just that.
Okay.
Okay, so now what's f prime of 0? What do we get when we plug 0 into that thing?
1/2.
Just 1/2. Perfect. Right? So our linearization is equal to f of 0 plus f prime of 0 times x minus 0, right?
Mm-hmm.
Just being super clear. So L of x is equal to, what's f of 0?
1.
1 plus
1/2 times x.
So there is our linearization. There's our approximating function. So what does that mean? That means that if you say, what's the square root at 0.01, or what do we get when we plug 0.01 into this? And maybe that's too hard for you to work with. You could instead use this function and get the value.
It gives you the same thing.
No, it approximates it. It'll be approximately the same thing.
Okay. And it's just x equals 0 for this problem.
It'll be approximately the same thing if we stay close to 0.
It can be the same thing though, right?
It can be the same thing,
Okay.
but it can be close to the same thing as well. So, that's the whole point. As long as you stay close to 0, then the square root of x plus 1 is roughly 1/2 x plus 1. Those give you roughly the same thing, as long as we stay close to 0.
Okay.
Make sense?
That's the equation of. Never mind.
And the author has some tables for values you plug in. So you plugged in x equal to 0.025. When you plug that into this for x, then you get 1.00002497. So that's what you get when you plug this value of x into there. What do you get when you plug into here? You get 1.00250. And look how close those numbers are together.
Yeah.
Super close. So, this is a good approximation of this as long as we keep our x's close to 0.
Okay.
What happens if the x's go away from 0?
The approximation gets worse and worse the further away we get. This tangent line only stays close to this curve. The tangent line and the curve are only roughly the same, close to the point where we found the tangent line. This is not a good approximation for this.
Yeah.
This is a good approximation for this.
Okay.
When does it go from being a good approximation to a bad approximation? It depends on what you care about for your specific problem. Okay, so now now let's find the linearization of the exact same function at x equal to 3. I guess. So when we switch x equal to 3, then what do we get? So f prime of x, that still stays the same thing, right?
Yeah.
But now f prime of 3 we need to figure out.
What's negative 1/2 of 4?
Negative 1/2?
Well,
Remember,
negative 1/2.
just, huh?
Keep going, sorry.
If you want to get rid of your negative exponent, just put in the denominator.
How do you put half in the denominator?
So this is the same thing as 1 over 2 times x plus 1 to the 1/2.
Which would be just 4.
It'd be what?
4. 1/4.
1/4. There we go. 1/4. So now, 3 there, 3 there, 3 there. For our linearization, what's f of 3?
2.
2 plus 1/4 times x minus 3, right?
Yeah.
Which is equal to, write my x first, so we have 1/4 x, and then we have 8/4 minus 3/4, leaves me 5/4. Did I do that right?
Yeah.
So there's our linearization. So close to 3, this is approximately the same thing as the square root of x plus 1.
For x equals 3.
For x close to 3.
Yeah.
Yes. At x equal to 3, though, giving the exact same thing. Okay.
Okay.
Let's do another one. Find the linearization of cosine of x at pi halves. So f of x is equal to cosine of x. We're looking for the linearization at pi halves. Right?
Mm-hmm.
Okay, so let's do it. What's f prime of x?
Negative sine of x.
Minus sine of x. Okay, so our linearization is equal to f of pi halves plus f prime of pi halves times x minus pi halves. Right?
Mm-hmm.
So, plugging in, what's f of pi halves?
0.
0.
Negative
F prime of pi halves?
Negative 1.
Negative 1. X minus pi halves. So what are we left with? It's equal to negative x plus pi halves. Right?
Yeah.
So there's your approximation for cosine, close to pi halves. So now, if someone asks you, what is cosine at something like 91 degrees, you have a way of approximating it,
Okay.
Gotcha.
right? Because you didn't really know how to do 91 degrees in this thing, but you do know how to do it into this thing now.
Okay.
Okay, so that's using linearization. Next, we're going to talk about differentials. Let's do our break now, and then we'll do differentials after the break.
Is this another lesson? Probably.
No, it's like the two halves of the same lesson.
This is the last half of the last lesson we're covering today.
Alright.
And then we have a test Tuesday, right?
Yeah, test Tuesday.
Okay, we're ready to continue?
Yeah.
Okay, so next thing we want to talk about is differentials. Now, we've already been seeing this symbol, dy dx is equal to blah, 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 blah. But the point is, we use this symbol to represent the derivative of y with respect to x. Right? Now, this was not dy divided by dx. This was a symbol for the derivative of y with respect to x.
Okay.
Right? If I knew that dy dx was equal to 7, I could then say dy is equal to 7 dx. It wasn't a quotient. It was just a symbol, the derivative of y with respect to x.
Okay.
With me?
Mm-hmm.
Okay. Now, with differentials, we are going to define symbols, dy and dx, and we're going to use them so that you can do this kind of stuff.
Okay.
All right? And we'll specifically define it so that dy dx, dy over dx, does give you the derivative, the slope, when it exists. So we're going to use a lot of these same symbols. It's a little bit weird that we're using the same symbols until you realize that we define these symbols so that you can still think about dy dx the way you already did. So let's get to the definition and you'll see. So definition. Let y equal some function in terms of x. Y equal f of x. And let it be a differentiable function. So you can take the derivative of it anywhere on its domain. With me so far?
Mm-hmm.
The differential dx, so differential, new word, haven't seen this before. The differential dx is an independent variable. Independent variable meaning you pick a number and plug it in. When y equals f of x, x is the independent variable, y is the dependent variable. So that's just going to represent an independent variable. We're going to plug in numbers for it. The differential dy then is defined by dy is equal to f prime of x dx. F prime of x is the derivative of our initial function, and it's going to be multiplied by whatever that number is. So notice that this has two independent variables to determine what dy, the dependent variable, is. Okay?
Okay.
So this is a variable, that's a variable, that's a variable. The value of this thing depends on the value of this and the value of this. Right? Now notice it is set up in such a way so that now if we do divide both sides by dx, then we get dy over dx is equal to f prime of x, which we expect.
Yeah.
So that's why we name these symbols the way that we name them, so that this still happens and it still works as you expect. So differentials, almost the exact same thing as working with derivatives.
Okay.
And the reason is because they're defined in such a way that dy over dx, that ratio, always gives us the same thing as the derivative, assuming it exists. Okay? So let's do an example with this real quick to try and help drive some points on. So if y is equal to x to the 5 plus 37x. First question is find dy. So what does dy equal then?
dy?
Yes, dy, the differential.
The derivative of that times dx.
It's equal to 5x to the 4 plus 37, all times dx. That's exactly right.
Oh, I see.
And notice that it's set up in such a way that now, if you would have written dy dx, that's equal to 5x to the 4 plus 37.
But aren't you trying to find just dy?
Yes, I'm just pointing out this to this. This is correct. We're done. Here's the answer.
Oh.
But notice it's defined in such a way that this would have been the case. Divide both sides by dx.
Okay.
That's aren't you supposed to find like the independent variable of dx? Or am I?
Dx is an independent variable. If I want to know what dy is, I need to know x and dx if I want to find a particular dy. So you did the first part perfect. That was the first part. Second part of the problem is now find dy when x is equal to 1 and dx is equal to 0.2.
Okay, I see.
So now what does dy equal in that case? So dy is equal to
42.
5 plus 37, 42, times 0.2, right?
Mm-hmm.
Or in other words, dy is equal to oh, come on. Times it by 2 and then move the decimal place.
8.4.
Yeah, you got that.
Right?
Yeah.
Okay. So there's your answer. Let's make sure we didn't make a mistake. 8.4. There it is.
Okay, I see how you do this now.
Okay. So that is what dy is. Now, geometric interpretation of the differential of this thing, dy equal to f prime of x times dx. Geometric interpretation of that, going back to our linearization, there's a reason that these are in the same section. This is just giving me the change in my linearization over some distance dx. So let me show you what I mean by that. So here's some function, f of x, right? And here is our linearization at the point A.
Okay.
So the change in our linearization over dx is this distance, whereas the change in our whole function was this distance, right?
Okay.
The whole point of this is going to be to notice that for small dx's, our dy basically gives us the whole change of the function. Again, we're going to use this for approximation. But, so this distance right here, this change in our linearization as we go from a to a plus delta x, let's calculate what that is real quick. So first off, what's our linearization? L of x is equal to f of a plus f prime of a times x minus a, right?
Mm-hmm.
Okay, now I want to know the change in my linearization from this point a to this point a plus delta x, okay?
Okay.
How do I get that? My change in L is equal to the value at a plus delta x minus the value at a. With me? That's this height.
So L of x is equal to?
L of x is this line.
Oh, so you didn't move
This is
from
f of x.
the top line to the second line.
Sorry, we should only have one line in here. We have our curve, and then our line. Everything else
I'm
is
not
just
saying you did your line in your image. I'm saying the two lines right there. Your two functions, your two equations. I'm saying, how did you go from one to the other? How did you go from L of x to delta of L?
No, we're going to calculate delta of L.
So why put L of x there?
So here's L of x, right?
Yeah.
And I want to find the change in L over this distance. What's my change in L?
Okay, I see what you do.
Which is this distance right here.
Mm-hmm.
I'm going to show you that that is d of y.
Oh, so you're proving it.
Yes.
Okay.
So our change in L, the change in this line, from a to a plus delta x, so over this distance,
Mm-hmm.
is just L at a plus delta x minus L at a. You follow that?
Yep.
Anything weird there?
And you're just substituting a into the equation of L of x.
Yeah, so L of x, here's the equation of L of x. I'm going to calculate L of x as change from this point to this point. How do I do that? I do the value at this point minus the value at this point, right? So that's all I'm doing. So the change in L over this distance, delta L, is going to be equal to L at a plus delta x minus, or dx, minus L times, or L at a. Good? Okay, so what is L at a plus delta x? Well, we just plug that in for x up here, right? So it's going to be f of a plus f prime of a times a plus delta x minus a. That's this term. This term is right here. Follow that?
No.
All I did was plug a plus delta x in for x into this equation. That's what got me this.
Well, how did you come up with the f of a and the f prime of a then?
A is a constant.
Yeah. Okay.
So look, what's L of 2? Looking at this equation, let's just find L of 2 really quick. L of 2 would be equal to f of a plus f prime of a times 2 minus a.
Yeah.
Okay, so here's what L of 2 is. Now what's L of a plus delta x?
Okay, I see it.
Replace 2 with a plus delta x.
Okay.
Follow it?
Mm-hmm.
Good. Okay. So here is L of a plus delta x. Now we need to do minus and then L of a. Now notice that when you plug a into this equation, what happens? This term goes to 0. So this whole thing goes to 0. So you're left with just f of a.
Okay.
So L of a plus delta x minus L of a.
Okay, I see it.
Follow that? Notice it makes sense that L of a is just f of a because what's the value of our line L at a? It's just f of a. So that makes perfect sense. Good? You follow everything we just did?
I think so.
You think so? What's making you only think so?
Trying to go from your third to the last one.
From here to here? Oh, well, f of a and negative f of a, those cancel out.
Yeah.
That a and that negative a, those cancel out.
Okay.
So we're left with f prime of a times dx. Which is exactly what we defined d of y to be.
Yep.
So this change in L is d of y, dy.
Okay.
So that's the geometric interpretation of what this gives us. What does dy give us? It gives us the change of the linearization across the distance dx.
Okay, I see that.
Okay? That's geometrically what it gives us. Okay. Now, for every differentiable formula, for every derivative formula, we also have a corresponding differential formula. So, what do I mean by that? So, what I mean by that is, we know that the derivative of u with respect to x plus the derivative of v with respect to x is equal to, well, oops, did that wrong. The derivative with respect to x of u plus v is equal to du dx plus dv dx. In other words, the derivative of a sum is just the sum of the derivatives.
Yeah.
We know that. So the corresponding formula, if we were just working with differentials, would be that the derivative, or d of u plus v is equal to du plus dv. Let's look at for product formula.
Why did you get rid of the dx?
Because we're not taking a derivative with respect to x. It's the differential of this is equal to the differential of this plus the differential of this. When you calculate the differential of u, then you would get a dx in there probably when we actually calculated it. So similarly, a more complicated one, if we do the differential of u times v, then that would be du times v plus dv times u with differentials.
Yeah.
Same way that the derivative of a product is equal to the derivative of the first multiplied by the second plus the derivative of the second multiplied by the first. Well, the differential of a product is equal to the differential of the first multiplied by the second plus the differential of the second multiplied by the first. How do you calculate a differential? We did that already. If y is equal to this, dy, the differential of y is equal to this.
But where's the dx in the formula for the function?
The dx shows up when we actually calculated dy. So when you actually calculate du, if you use a function in x, when you actually calculate du, that will have a dx in it.
Where does it come from and where does it go?
Look, we can view this as a function plus a function.
Yeah,
So that's like looking at this top case.
yeah.
I can call this right here u, and this right here, or sorry, this u, this v.
Okay.
So then, what's du? If we want to write this out the long way, y is equal to what's du? That's 5 times x to the 4 times dx plus 37 times dx. Okay, so if this is u and this is v, this is du, this is dv.
Okay.
So where's my dx? It comes when you actually calculate that thing.
Okay.
Because y, I could have also said this is equal to u plus v, right? And so dy is equal to du plus dv.
Could we see an example of the multiplication?
Yeah. Not multiplication, chain rule, and then quotient rule. Okay, so calculate the differential of tangent of 2x. So what's the derivative of 2x, or tangent?
Secant squared.
Secant squared. So this is going to be secant squared of 2x times 2, and then times dx.
Where did you get the 2?
Derivative of the inside, chain rule.
Okay.
Good?
Yeah.
All right. Now let's do the differential of x over x plus 1. Good? All right. So we have the bottom times the derivative of the top,
Just x plus 1 times 1
dx.
times, yep, okay. Plus,
Minus.
minus, x times
dx
dx, yep.
over x plus 1 squared.
So that's equal to, let's distribute it out. We're going to have an x dx and a negative x dx. Those go out, leaving me just plus 1 dx. So it's just going to be dx over x plus 1 squared, which is what they have.
Okay.
Okay? All right. Looking back at our picture now, when we're using differentials for approximating, then notice that dy is almost a change in the height of my actual function.
Yeah.
Yeah.
So we're going to use these differentials to approximate change in heights of functions as well.
Okay.
And as long as our dx isn't too big, then our dy almost gives me the whole change in the function. Right?
Yeah.
Notice that if we were looking about like right here, dy and the change in the actual height of our function are pretty close to the same thing now.
Yeah.
So that's one of the places where they're often useful is for calculating approximations. So let's do an example with that. The radius r of a circle increases from 10 meters to 10.1 meters. So r goes from 10 to 10.1 meters.
Okay.
Use dA to estimate the increase in the circle's area, A. Estimate the area of the enlarged circle and compare your estimate to the true area found by direct calculation. Okay, so area of a circle is equal to, what's the formula?
Pi r squared.
Pi r squared. So dA is equal to,
D of A is,
r is going to be our independent variable here.
so what, 2 pi r
2 pi r
Yes.
dx. dA.
DR.
dr. R is our independent variable now.
Okay.
Okay. Now, this is our change in area. Our dr up here is equal to 0.1. That's our change in our radius, going from 10 to 10.1, right?
Mm-hmm.
So that's our dr, and our radius is 10. So the change in our area should be approximated by 2 pi times 10 times 0.1. That's a times 0.1, maybe that helps it read better. Is equal to what?
2 pi.
2 pi. So our area changed roughly 2 pi when our radius went from 10 to 10.1.
What? How does that work?
So the area of our circle before, so now let's just calculate it by the horns and see how good our approximation is.
Okay.
Okay? So what is the area of a circle when we plug in 10 for the radius? What exactly is the area of a circle when our radius is exactly 10 meters?
Pi times 100.
100 pi, right?
Yeah.
Yeah.
Okay, what is the area of our circle when we plug in 10.1? Exactly.
100.1.
What's 10.1 squared? So we have 10.1 squared. That's 102.01. 102.01 times pi. So this is the area of a circle with radius 10. This is with 10.1. Exactly. Using the area of a circle formula, right?
Mm-hmm.
So notice that in reality, if you take your circle and you increase the radius by 0.1, then you really increase the area by 2.01 pi. What did we approximate? 2 pi. Notice how close that was.
Yeah.
We said it should increase by roughly 2 pi, it increased by 2.01 pi.
Okay.
So that's what our approximation gave us.
Okay.
Make sense?
Mm-hmm.
So let's do another one. Use differentials to estimate the cubed root of 7.93. So we're trying to approximate 7.93 to the 1/3.
Okay.
Now, what's the function that we're using? The function that we're using is x to the 1/3, right? So we'll call that f of x. So what's f prime of x?
1/3 x to the negative 2/3.
Right?
Mm-hmm.
What's the value that we know how to calculate this of real easily?
What do you mean by that?
What number x do I know how to take the cube root of real easily? That's close to the number here.
8.
8. Right? The cube root of 8 is 2. So 2 is what we're doing our linear approximation around.
Okay.
But you have to infer that from the problem?
Sorry, we don't want f prime of x. Sorry, let's call this y equal to this. We're doing our differential. Yeah, you needed to just know, oh, that's really close to 8. You need to see that in your head. So what is dy now equal to?
dy?
Our differential, yeah. We calculated derivative. I meant to do differential.
Well, 1/3 x to the negative 2/3 times dx.
Times dx, okay. So the important part being that dx there.
Yeah.
So now, our dx that we're going to use, so our x that we're going to use is x equal to 8. And our dx that we're going to use is negative 0.07.
Why negative 0.07?
Because that's going to get us to here.
Oh, I see.
That's how far away this is from the value that we knew how to calculate, right?
Mm-hmm.
So, our value, f of 7.93, is going to be roughly approximated by our value, f of 8 plus dy, plus our change.
dy, yeah, dy.
So what is our dy? 1/3 times 8 to the negative 2/3 times negative 0.07.
Okay.
Right? So let's calculate that. Let me write it one more way to maybe help you. So in the numerator we have negative 0.07, and that's divided by 3 times 8 to the 2/3.
Yeah.
Okay. So now we can calculate that. Negative 0.07. 8 to the 2/3 is 4.
What?
Cubed root of 8 is
2.
squared.
4. Is that how you solve fractions?
Uh-huh. Remember, 8 to the 2/3 is the same thing as 8 to the 1/3 squared, or however way you want to think about it. You can think about it as 8 to the 1/3 squared. Doesn't matter. It's easier to think about this way in this case.
Well, still, what's 8 to the 1/3?
2.
2
Because 2 times 2 times 2.
is 8.
Oh. Okay.
Okay. Anyways, so yep, 4, so 4
12.
times 3 is 12. Right? Negative 0.03. Oh, I read the problem wrong. This is 7. So this is a 3. So 3. We could have just kept doing what we were doing, but I just want to make sure that all the authors don't make any mistakes. 7. Okay. So our value can be approximated by f of 8 plus dy, which is equal to, what's f of 8?
2.
Just 2. Plus, whatever this value is, it's really going to be minus a little bit. obviously it should be slightly less than 2, right?
Mm-hmm.
So we plug in negative 0.03 divided by 12, and we'll just look at the author's approximation. Oh, he doesn't give us his approximation, he just has it when he has it all added together. So when he adds it all together, he gets 1.9975. So that's after he already subtracted it. Okay?
Yeah.
So there's our approximation for this value.
And you're expected to find, like, the 8 in this case?
Yeah, you were expected to be able to come up with, okay, I know it's 8, this value, whatever this value is, it's the same value I would get at 8 plus a little bit.
So all our homework is going to give us is just that one number, the 7.97 to the third, right?
And the x.
It,
Well, no, we give the x.
Yeah.
it would give you this, the problem was approximate this.
Okay.
So step 1, come up with the function that we're talking about.
Mm-hmm.
Step 2, come up with the point that is close to it, that's easy for us to work with, and how far we are away from that point.
And then just do the math from there.
And then calculate your differential, that's your change, so that's your change from the point you like. So here's the point you like, plus your change gives you your approximation.
Okay.
Make sense?
Mm-hmm.
Okay. So let's do another one. This is part B. So for part B, just write down here. We now want to approximate the sine of pi 6 plus 0.01.
Okay.
Plus a little bit. So notice we know what pi 6 is. Here's a little bit that we're dealing with. So the x that we know what this is around is pi 6, and our dx is going to be
0.01.
0.01. So our differential of this is going to be what? So dy, we'll say y equals this. So dy equals what? Just cosine of that.
Times dx. Don't we have to split it?
Sorry, our y is going to be, what's our actual function? Sorry. So this is what we're approximating. Our function is y is equal to sine of x. That's the function we're using.
Mm-hmm.
Sorry. Now, our differential dy is equal to cosine of x times dx.
Yeah.
Yep.
Right? So, dy is equal to, in our specific case, that's going to be cosine of pi 6 times 0.01, right?
Times or plus?
Times.
Why is it times? Oh.
Derivative of the outside times the derivative of the inside.
Okay.
Okay? So, this is our dy. This is equal to, what's cosine of pi 6?
Root 3 over 2.
Root 3 over 2 times 0.01. Right?
Can we not simplify that any further, or just leave it there?
We could if we want to. I mean, this
But
is the
it'll
same
probably get
thing
messy.
as 1/100th, right?
Mm-hmm.
So I can view this as times 1 over 100, and then I can say root 3 over 200.
Okay.
Okay? So now, that's our dy.
Okay.
So our value, sine at pi 6 plus 0.01 can be approximated by sine of pi 6 plus dy. right?
Mm-hmm.
So this is going to be, what's sine of pi 6?
Root 3 over 2. I mean, it is 1/2.
1/2. 1/2 plus root 3 over 200, which is equal to, if we want a common denominator, 100 plus root 3 over 200.
Okay.
Let's see what they get. They didn't write it like that. They get, we got the same thing, but the numeric approximation is 0.5087.
So if you would plug that into a calculator.
Slightly more than 1/2. Yeah, if you plug this into a calculator, you should get roughly that.
Okay.
So there's our approximation. Make sense?
I think so.
Okay. Proof of chain rule, we don't need to do proof of chain rule. Let's do another one. You want to calculate the depth of a well from the equation S is equal to 16t squared. Okay, so going to use some approximations, figure out our margin of error in our guessing, to guess the depth of a well. So the problem that we're setting up is we're going to try to figure out how deep a well is by dropping a rock into the well. And we're going to use the fact that we know that S position is roughly 16t squared.
Yep.
Good?
That's just gravity, right?
Yeah, when you do it in feet per second, or when you do it in feet and use feet and seconds as your units, then this is the equation for a falling object. So S is equal to 16t squared. So you want to calculate the depth of a well from the equation S equal to 16t squared by counting how long it takes a heavy stone you drop to splash into the water below. How sensitive will your calculations be to a 0.1 second error in measurement? So our error is 0.1 seconds. We're going to say that we can't tell better than within a tenth a second what our time is that this was actually falling for. Right?
Mm-hmm.
Yeah.
Now it's going to depend on how the time that we actually calculate. How much the error comes into effect will depend on how long it actually takes the object to fall. You'll see what I mean. So first off, let's calculate the differential of S. What's that equal to?
32t
32t
times d of t.
times d of t, which d of t is going to be that. Okay, so the size of ds in the equation, this depends on how big t is. If t is equal to 2 seconds, the change caused by d of t equal to about 0.1 is, we'll see. So, set up the scenario rather than just falling from. So let's imagine that I now drop my rock and my stopwatch, I time it, is 2 seconds.
Okay.
2 seconds. So you're tempted to say, okay, it took 2 seconds, so how deep is the well?
64 feet.
64 feet is what you're tempted to say, right?
Mm-hmm.
But the problem is we only knew that within 0.1 seconds. So what's a margin of error on our measurement of the depth of the well?
0.
You see what I'm saying?
Yeah.
No, that was in the time. What's our margin of error in the depth?
Oh, that's what we're trying to find.
That's what we're trying to find. So if it took 2 seconds, so if t is equal to 2, then our margin of error, our change in ds would be equal to 32 times 2 times 0.1,
64 times 0.1.
which is equal to
6.4.
6.4 feet.
Oh, wow.
So it's 64 feet plus or minus 6.4 feet. That's how well we know the depth of the well. Make sense?
Yeah.
And then, let's say that instead we thought that it took 5 seconds to fall. Let's calculate our margin of error then.
Okay.
So, 5 seconds. What would we expect the depth to be?
400.
400. So we expect S to be approximately 400 feet, plus or minus, let's figure out our error. So our error now is 32 times 5 times 0.01, which is equal to
5 times 32. 160. 16.
16. So it's 400 feet plus or minus 16 feet would be the depth of the well.
Okay.
So that's our margin of error. So we can also use this to calculate our margin of error,
That's pretty cool.
if we know the margin of error in our initial. Okay, so there we go. That finishes up the section,
Okay.
and that finishes up the chapter. So you have the rest of class to get going on homework, and we'll do tests next week.
Do you have time to go over questions?
Yep.